So this is a little simulator. It's an orbital simulator. So we've been looking at orbits. Let's pretend here is the sun, here is the Earth. If I start this sim running, one of the things that you notice, and we normally tend to take it for granted or ignore it, but can you see the sun's got a bit of a wobble? Now this is really exaggerated for the Earth, but this is how we found the very first exoplanets way back in the mid-90s. We found stars way out there that had unexplained wobbles, but the wobbles were periodic. They had repeated, and that allowed us to figure out not only that there was an exoplanet out there, but if we knew the period, we could make a pretty good estimation as to what the orbital radius and what the orbital speed was. But we only saw stars wobbling if the planet that was orbiting them was massive, like Jupiter size or bigger, and it had to be really close. It couldn't be way out there. So this limited what we could find. But still, that's not a bad sim. Let's bump it up to a sun, a planet, and the moon. This is one of my favorite. So here's the sun. Zach, here's the Earth in purple, and there's the moon. Try and imagine what it looks like from the top if you were staring down at our solar system. What would it look like? What path would the moon trace out as it orbited the Earth? You ready? Most people don't think that. In fact, I see a bunch of you smiling because, yeah, Paige, it's a nice result. You can imagine the early astronomers when they were calculating and graphing these by hand. There's a reason they talked about the music of the spheres or the cosmic dance. It really is kind of a pretty little picture. That's the picture of something moving in circles around something else that's moving in a circle. What else can we have? We could have comets. So usually a comet is in a stable orbit until for some reason it passes near another object that deflects it slightly. Then its orbit will often be decaying, and eventually most comets end up, well, the sun is kind of the great cosmic vacuum cleaner. And so probably this comet, after a few more orbits, will end up in the sun, because every time this purple planet's coming by, it's deflecting it ever so slightly.
Couldn't it technically hit us?
Pardon me?
They could technically hit Earth.
They can. Comets aren't that dense. They're mostly very, very almost gaseous ice and some dirt. But yeah, we're not special. If you saw Star Wars, Tatooine, where Luke Skywalker grew up, has a binary star. We can model that mathematically. So the light blue is the planet, and the purple and the yellow are the binary stars. It would be a little bit interesting, for example, if I pause it right here, and if I take the traces off, right now, the planet would have no night. It would be daylight everywhere. So is it possible for life to exist there? Don't know, but we can certainly model that. There's no reason why there couldn't be something like that out there somewhere.
Do we really need night that much?
Pardon me?
Do we need night that badly?
Do we need night that badly? This planet probably would not have any liquid water. It would have boiled away. So really, let's rephrase the question. Do we need water that badly? Helps. Trojan asteroids. Our sun has an asteroid belt. It's where a planet just tried to form and never quite could. And so you can have asteroids that are in stable orbits. You can also have asteroids that are not in stable orbits that might hit us. We know of at least one that came and wiped out the dinosaurs, is our best explanation for that. You could have 4 stars orbiting each other. Now, the likelihood of this occurring in nature is pretty slim, because this is not a very stable arrangement. This one is. If we saw this, we might suspect that some cosmic intelligence with far more technology than us had set it up. Because if I reset this, and if I move one of these stars even just a little bit, the odds are pretty good that this won't be stable at all. So for you to get a stable 4-star ballet, highly unlikely that it happened by chance. Could? Unlikely. Slingshots. We use gravitational slingshots all the time when we send probes, especially to the outer planets. What we do is we have the probe come close to a planet and use that planet's gravity to accelerate it. And technically the planet itself slows down a tiny bit, but the planet has such a big mass, its slowdown is negligible. So if you watch close, this light blue is the satellite. It's going to go past this planet, and it's going to pick up some speed. You have to watch because it happens really quick. Wait for it. Right there. We picked up some speed from that planet. It's a little tough to spot, so here's a double slingshot. This light green is our probe. If you watch close, it's going to pick up speed from this and pick up speed from this. We've done orbits where we've had 5 or 6 slingshots, really, really beautifully done, using Venus and Mars and Earth to get way more speed than we could pack in just with the rocket fuel. There's the first slingshot. There's the second slingshot. It happened fast, so watch again. There's the first one. There's the second one. It just gained some speed from the other planets. We yesterday looked at circular orbits. Orbits can also be elliptical. However, if we ever see an object that comes by with a hyperbola, those of you in calculus that have done hyperbolas, if we ever saw a hyperbolic path, that would tell us that this was an interstellar object, that this came from outside of our solar system. Until about 3 years, I always said, and we haven't found one yet, but about 3 years ago, we found an odd, long, narrow object. It has a long name that starts with letter O. It's in the Hawaiian language, so it has lots of vowels and consonants. But that one was tracing out a hyperbolic path. That was the first official interstellar object that we've ever spotted. We know it came from outside of our solar system. Most orbits are elliptical. We're looking at circular ones. Most of the orbits of the planets, though, are much closer to this purple one. This purple one looks like a circle. It's not. So one of the reasons why it took astronomers so long, really until just before Isaac Newton, it was Kepler and Copernicus who figured out that orbits are elliptical. It was because they were so circular that, and it was logical to assume they were circular. People assumed the glitches were just observational error. They didn't trust their observations. And it wasn't until Kepler came along, he proved actually elliptical orbits are what we're seeing. You could have 4 planets orbiting each other, where 2 planets are orbiting each other and 2 other planets are orbiting each other, but the center of masses of each orbits are also orbiting each other and it's stable. Again, if you saw something like this, we'd be pretty sure, Emrit, that it was artificial, because if this is even slightly off, you don't have a very stable 4-star or 4-planet orbit. This would suggest to us that some other intelligence had set that up somehow. So there's what some different orbits can look like. That's the orbital app. Let's talk about orbital, Terran, or cosmic potential energy. You guys with me? George, we can't use PE equals mgh in outer space. Why? Oh, hang on. Someone at the door. GH? Yes, G is changing. Okay? So we have to go to a different definition of work and energy. Recall, the area under a force versus distance graph is work. In other words, if this graph is force, this graph is distance, I'd like you to draw a line that goes up slanty like that. But then on the x-axis, I want you to put a little x1 right, actually put a little lowercase a right there, and a lowercase b a little further on. And kind of shade that area in. the area underneath this graph is actually the work needed to move a mystery object from location A to location B. How much energy did it take? How much work did it take? Whatever that area is. We talked about that in the work energy unit. I didn't hugely emphasize the graphs because you folks didn't see energy last year because of COVID. Normally I do, but I'm going to tell you this is the area, this area is the work required to move an object from location A to location B. Let's see if we can apply that to a different force, to gravitational force. So if I have Fg versus R, first question is, what's that graph going to look like? Well, I know Fg equals big G, big M, little m over R squared. I'm going to argue if we ignore everything but the F and the R, Fg is going to be similar to 1 over R squared. That's what it's going to look like. You don't graph R squared much. You know what you graph an awful lot in math? X squared. What is the graph of y equals x squared? Start with the letter P. This is going to be the reciprocal of a parabola. Those of you that have done pre-calc, you have done the reciprocal transformation. You did do that. What would the reciprocal of a parabola look like? Kinda like that. That's what a graph of gravitational force versus distance r from the center of the planet would look like. It would not be a line, it would be a curve. The further away you get, the weaker gravity gets, but the change is biggest at the beginning. We're going to combine this notion and this notion. So consider, suppose I have gravitational force on the y-axis, r on the x-axis, and Zach, that's a graph that's going to look something like this. Right about here, I'd like you to put a point and call it our Earth. Right about here, I'd like you to put a point and call it our orbit, short for orbit. And then, just like before, I'm going to draw a little dotted line, a little dotted line. This area here is what we're talking about. This area equals the work needed to lift an object from our Earth to our orb. This will allow us, George, to avoid MGH because we can't use it anyways. But we got a problem. Don't write this down. How do I find the area of a curvy shape like that? Well, calculus. But some of you aren't in calculus. And even those of you that are, you haven't done areas yet. You'll get to it. Okay. I'm going to do some bad math, but it's going to get us to the right location. So I'm going to say, indulge me. Since work equals force times distance, I guess we can say this. Work equals gravitational force times R, based on that graph I just drew. What's the equation for cosmic gravitational force, Gabor? Big G. Okay. So I can take this. This is going to become big G, big M, little m over R squared times R. Huh. What happens to one of the R's? One of the R's cancels. Now, this is the work done in lifting. You know what another word for the work done in lifting is? Something energy. This is potential energy. So, this is going to give us an equation. Look up. Don't write this down just yet. It's called the tension span. You can focus here. Look. Somebody else at the door? Oh, we got more people. Don't write this next bit down. Here is the equation for cosmic potential energy. It equals big G, big M, little m, over R, but it's negative. Write that down. And then once you've written that down, please find it on your formula sheet, because I'm pretty sure I gave it to you. Yeah. You can see, Paige, it kind of came out of here, sorta. Big G, big M, little m over. It's sort of out of force times distance. But why negative? Okay. Calculus students, it's negative because if you take the derivative of this with respect to R, you'll get gravitational force. You can try it sometime if you're bored. So if you go PE equals big G, big M, little m times R to the negative 1, and you move the exponent, oh, there's a negative there, move the exponent to the front, the negative times negative cancels out, you'll get an R to the negative 2, which is an R squared. I can't say that to the non-calculus students. Okay. If I lift something up and I let it go, what happens? It will, it falls. Why? Because it has potential energy. You with me so far? What if I let something go and it doesn't fall? How much potential energy does it have? As a number exactly, 0. Where will we have no gravity? Where will we have no potential energy? Out at the edge of the universe. In fact, we're going to say out at infinity. Calculus students, it's a limit. Out at infinity. You will have no potential energy out at infinity because there's no gravity out there. So we use a phrase, we call it relative to 0 at infinity. Here's what that means. I'll take your questions at the end. Suppose this is the surface of the Earth and I want to get this all the way out to infinity. Once I get it here, how much energy will it have? 0. We've defined 0 to be out at infinity. So for me to get it to there, though, I would have to do work. I would have to add energy, lifting, to get to 0. If I'm adding energy to get to 0, what kind of numbers must I be starting with? Negatives. We had to define 0 energy somewhere, and we decided we're not going to define 0 energy to be the surface of the Earth. That's too egocentric, and that's not helpful for going cosmic. You know where 0 energy is? Out at the edge of the universe where there's no gravity. Or those of you that might recall Einstein's version of gravity, where the gravitational sheet of space-time is completely flat. That's 0 gravity. Anywhere else, you're in a pit of gravity, you've got negative energy, and you've got to burn energy to get back to 0. Aiden, you had a question?
How do we know 0 gravity up there? We've never been there.
Because are you in calculus? If you look at the gravitational force equation, as R gets bigger and bigger and bigger and bigger and bigger and bigger and bigger, what happens to the force of gravity? It gets smaller and smaller and smaller and smaller. What if R was infinity? 0. That's how. It's a calculus limit.
So if you had a planet down there, that the gravity hurts.
Well, if we had a spacecraft out there, the spacecraft could shut off its engines and it would just stay there. Okay? So why negative? Out at infinity, at the edge of the universe, an object would have 0 potential energy because it can't fall, because there's no gravity field acting on it. If our height is less than infinity, we have less potential energy. What numbers are less than 0? In fact, we use the phrase relative to 0 at infinity. That's our hint, Sarah, to say to you, don't use MGH. Use the cosmic version of potential energy. Sometimes we'll even abbreviate it. Relative to 0 at infinity. I think once or twice in the homework I put that little acronym in there just to remind you. Yeah, but use the cosmic one, please. I like example 1. I like example 1. I like example 1. Example 1 is a nice question. A mass is released from a height of 6,300 kilometers above the Earth. How fast will it be going when it hits the ground? Ignore air resistance. Dharma, what's this question asked me to find? Okay. When we drop this, will there be a change in speed? Yeah. Will there be a change in height? Yeah. Will there be a yucky, curvy force? This is a job for conservation of energy. But we're going cosmic. So it's going to start out the same as before. P E initial plus K E initial equals P E final plus K E final. Are we cosmic right now? Are we in outer space? Then I can't use MGH. Okay. Are any of these 0? Well, it says released, so I think I can say we're dropping it. Where will potential energy be 0? If we're cosmic, only if we're out at infinity. Are we starting out at infinity? Now, in real life, by the way, Aiden, what I'll probably say is starting a very long ways away. That's my code for, well, we're not out at the edge of the universe, but we're far enough away that whatever gravity is negligible. 0. Well, our new potential energy equation is negative big G, big M, little m over R initial equals negative big G, big M, little m over R final plus kinetic energy hasn't changed. It's still a half little m V final squared. What was that? It turns out the impact speed doesn't depend on mass. Impact damage does, yes, but a massive asteroid, if we're ignoring air resistance, and a tiny little meteorite, if we're ignoring air resistance, they'll hit the ground with the same speed because the little m will cancel. What are we trying to find? This is where my love for getting things by itself ends. In fact, I'm going to advise a very bizarre procedure. First thing I'm going to do is I'm going to get the 0.5 v squared by itself. I'm going to plus this to this side. It's going to look like this. Negative big G, big M all over R initial plus positive big G, big M over R final. That equals 0.5 v squared. One of the things I probably should have done, that 6,300 in the original question, why does that creep me out? Kilometers. How do we go from kilometers to meters? So I should have really said, I think this is 6,300 times 1,000, and I probably would have written in scientific notation as 6.3 times 10 to the 6th. Okay. Oh, what's the word next to that 6.3 times 10 to the 6th meters? What does that mean? I'll have to add the radius of the Earth. We're dropping it from here. Okay. Negative. What's big G? Put your calculator down. Don't start typing. What's big G as a number? 6.67 times 10 to the negative 11. Big M, mass of the Earth. 5.98 times 10 to the 24th. Our initial, 6,300 kilometers above the Earth. That's going to be 6.3 times 10 to the 6th plus the radius of the Earth. 6.38 times 10 to the 6th. Plus, wait a minute. Paige, what letter is this right here? Big. What letter is this right here? What letter is this right here? What letter is this right here? Because we're going to be doing so much writing and typing, I'm going to use quotation marks or ditto marks. I'm actually going to go same thing times same thing divided by, what's our final? No, that would be the very center of the Earth. I don't think we're getting there. Where are we hitting? Starts with the letter G. So what's our final? More specific. What's our final? More specific. What's our final? What? That equals 0.5 the final squared. Write that down. And then I'm going to insist that all of you follow me exactly on your calculators, because we're going to try and...
Why are there two underneath the left one? The 6.3 times 6 and 6.38.
Okay, so you were away yesterday. They gave us the altitude, which is that. I need the radius from the center of the Earth, so I've got to add the radius of the Earth to the altitude to get the total radius. Everybody get your calculator out. Once you've written the numbers down. No going ahead. Zach, got your calculator out? Good. Clear. Negative 6.67, scientific notation, negative 11, times 5.98, scientific notation, 24, divided by, or you could be using your fancy schmancy fraction button. Is there more than one thing on the bottom? I have to open up a bracket. 6.3, scientific notation 6, plus 6.38, scientific notation 6, close off the bracket, and stop typing. There is so much typing, and I learned when I used to make the kids type everything, we got typos all the time. So instead, what I'm going to say, Paige, do you notice the tops, the numerators of the two fractions are identical? Type the first term in really carefully, hit equals. And all of us right now should have negative 31456309.15. Yes? I'm going to write this down to about 5 sig figs. Negative 3.1456 times 10 to the 1, 2, 3, 4, 5, 6, 7. I'm going to write down negative 3.1456 times 10 to the 7th. And then I'm going to drop the plus sign down. I'm now going to backspace. Bring back the previous calculation. I guess I need to get rid of the negative in the front. Done. What else do I need to get rid of? Done. Now I've got the second term with way less typing and way less chance of me making a typo. The second term is 6.2518 times 10 to the 1, 2, 3, 4, 5, 6, 7. If you didn't get those numbers, you made a typo. We'll get it next time. That equals 0.5 v squared. Now I'm going to solve the question. The first number is negative 3.1456, scientific notation 7, plus, answer button, right? I'm going to hit equals. The whole left side works out to that. How would I get the v by itself? You said divide by 2 and divide it by a half. One of those, I think you're going to divide by 0.5, not by 2. That gives me v squared. And I get it's going to hit the ground at 7,880 meters per second, which is right. This trick here of using ditto marks and then just backspacing and editing, we're going to use that like crazy. That was not the question that I warned you about that we would do the most writing on. I like example 2. I like example 2. Example 2 is a nice question. What was that? Is it though? No, I didn't say that. I just said I like this question. What was that? What if the earth is full? I do know. Zach, what are they asking me to find in example 2? Work. Why can't I go work equals force times distance? This only worked when the force was constant. What does gravitational force look like? Curve. Work is also the area under a force versus radius graph. Zach, did they give me a graph? What was the third definition of work, what we called the work energy theorem? It's on your formula sheet. In the energy section. Work equals change in potential plus change in kinetic. Zach, what word did I underline? So here's what you want to imagine. Here's my satellite. It's starting out on the surface of the Earth. How fast is it traveling before launch? Be obvious? 0. And now we're holding it there. How fast is it traveling after launch? Be obvious? 0. When we're just lifting an object, does this anywhere say the word orbit? Then we're going to assume that we started and ended at rest. Zach, what's change in anything? Good. So the work is going to be PE final minus PE initial. Oh, this is easy. I can go MGH final minus MGH initial, can't I? Why not? We're cosmic. So Zach is cleverly realizing we're going to have to use our cosmic potential energy equation. What is our new cosmic potential energy equation, Zach, my friend? Read it to me, please. And I guess since it's potential energy final, our final, minus negative big G, big M, little m, all over our initial. There is a minus minus in the middle that's going to become a plus on the next line. Work is going to be negative. Zach, what's big G? Big M. Little m. Read the question. Little m. Yeah. Wait a minute, Mr. Dewick. There's an m here and an m here. Don't they cancel? Is there an M in work? Of course they shouldn't cancel. It should take way more rocket fuel to put a bigger satellite up than it should put a smaller satellite up. 1,200. What's our final? They didn't tell me. You know what they told me? A word that starts with letter H, Zach. A word that starts with letter H, Zach. A word that starts with letter H, Zach.
Oh, height.
Thank you. They told me the height or the altitude. How can I change a height or an altitude into a radius? I'm going to end up adding the radius of the Earth. So it's going to be 1.2 times 10 to the 7th plus 6.38 times 10 to the 6th. Then, Zach, I see a minus minus, which is a... Yep. And then, oh, Zach, what would I write next? Big G? What's on top over here? Big G? And then I would write mass of the Earth. What's on top over here? Mass of the... And then I would write little m. What's on top over here? Also, what? Little m. You know what? I'm not going to rewrite them all. I'm going to go same thing times same thing times same thing. By the way, in university next year, they probably won't let you get away with this, but I wish they would. Is our initial going to be the same? No. Where do we start? Surface of the Earth. So what's my radius? 6.38. To the 6th. Now, if you want to, you can type both of these fractions all in at once. What I'm going to do is type the first fraction. Hit equals. Write that answer down to, usually I go to 5 or 6 sig figs. Then I'm going to backspace edit, get the second fraction to 5 or 6 sig figs. Then I'll add them together. Oh, and the W is already by itself, Zach, so that's a bonus. I don't have to do any hard thinking. That's why I gave it to you. Oh, no, that came out wrong. Oh. Look for typos. looks good. I think for the first term I got negative 2.6041 times 10 to the 10th. Plus backspace. And in case you're wondering, it was this unit and this particular question why I yelled at all of you last year to get a good calculator that would let you backspace and edit. Because I think I just need to delete the negative and delete the 1.2 times 10 to the 7th. And I get plus 7.5022. Times 10 to the 10th. Zach, when we launch this, when we lift this, will we have to do work, or will it want to fall that way on its own? Will it want to fall up? Yeah, you do. Be honest. Will it want to fall up on its own?
No.
No. So here's what that means. We will have to do work, which means we should get a positive answer here because we're going to have to add energy to the satellite. Are we going to get a positive answer? Garrett shook his head. We are. If you're careful with your signs, you'll almost always get a minus minus, which is a plus. And you'll get a positive answer when you need a positive answer. So that whole negative in front of the term, don't let it panic you. It'll take care of itself. In fact, it's going to be negative 2.6041 times 10 to the 10th plus answer button, because I'm lazy. And I get 4. Now I'll go to 3 sig figs for my final answer. 4.90 times 10 to the 10th joules. Just to give you a ballpark figure, usually if you're calculating how much work, how much rocket fuel, how many joules to send a satellite into orbit, if it's around the Earth, it'll be in the 10 to the 10th, 10 to the 11th range. Maybe 10 to the 9th if you're sending it way out there. But usually in the 10 to the 10th range. Are we in the 10 to the 10th range? I probably did this right. Oh, if you're ever doing a question around the moon, totally different. This satellite has no kinetic energy. What that means is it will just fall back to the Earth. Splat. To lift an object, we only need to give it potential energy, gravitational potential energy. But to put an object in a stable orbit, not only does it have enough potential energy for me to get to the right height, I also have to give it what kind of energy to get it so that it's always missing the Earth in free fall? The energy of motion, which is called what? You're right. Kinetic. Here it is. Longest question of the year, example 2. I like example 2, I like example 2, I like example 2. Example 2 is a nice question. How much work is done placing a 925 kilogram satellite in orbit? I would probably underline the phrase orbit. That tells me I have a lot more tools at my fingertips. With an orbital radius of 2.6 times 10 to the 7th and an orbital speed of 3,917 meters per second. Nick, what's this want me to find? Well, I might try force times distance. Wait a minute. Are we cosmic here? Will the force be constant throughout this, or will it be getting weaker the further we get from the planet? Weaker. So, Oh, it's also the area underneath the force resistance graph. Yes? Will that help? No graph. What's my third, more cumbersome but best definition of work? In the previous question, because we were lifting, the change in kinetic was 0. Are we just lifting it, or are we keeping it in orbit? That means we have to give it some kinetic energy so that it is always missing the Earth. None of these will cancel. However, I would recommend you find one of these at a time. So, Nick, would you like to find the change in potential or the change in kinetic? Don't care. Change in potential? What's change in anything? Okay. What's our cosmic potential energy equation? Our final minus negative big G, big M, little m over our initial. Okay. Negative. Nick, what's big G? Good. Big M. If the question doesn't say, assume Earth. 5.98. Little m. All over our final. Is it radius of the Earth plus 2.6 times 10 to the 7th? They didn't give me an altitude. You know what they gave me? An orbital what? That's the radius. 2.6 times 10 to the 7th. They didn't give me an altitude, so I don't need to add the radius of the Earth to it. Minus minus is up. Are you positive? What can you say about the top of this fraction compared to the top of the previous fraction? Same thing times same thing times same thing divided by our initial. Okay. And now I'm going to go to my calculator. I'm going to do the same thing I did before. Do the first term very carefully. Write it down to 5 sig figs. Then backspace and edit the second term also very carefully. Write it down to 5 sig figs and then add them together. Let's see. Let's see. Ooh, almost. No, never mind. Yeah, I did make a typo. It's not plus 5.98, it's times 5.98. And I got a mismatched bracket. Are we ready? I thought I had an error. I've typed something wonky here. For the first term, I got negative 1.419 times 10 to the 10th, which seems ballpark right. And then plus, I should be able to backspace. Get rid of that. I get 5.283 times 10 to the 10th. 5.78. Did I say 28? Can't even read. 5.783. 5.7829. 5.7829 times 10 to the... And now I'll get an answer for the change in potential. Negative 1.419. Scientific notation 10. Plus, haha, answer button. I got 4.96 times 10 to the... You know what? I can't read right now for some reason, but is this my final answer? I'm going to carry 5 sig figs. That's why I wasn't being that careful. It's going to be 4.3639 times 10 to the 10th. Aiden is discovering what the most common mistake is. It's going to be typing. This is heavy-duty typing. What was that? No, I thought Mud said something. Okay. We're not done. Not even close. I wish.
What?
What else do we need to find? We've just found the change in potential. What's changing anything? Okay. I figured you would.
It wasn't. It was my top. It was the.
Yeah, I stopped caring.
A bracket. I didn't need a bracket.
Whatever.
But
Are any of these 0? Well, if we're in a stable orbit, can we ever be at rest in orbit? No, we actually said yesterday V orb had to be the square root of big G, big M over R. There has to be a sideways speed. So I know V final isn't 0. What about V initial before launch? What's that? Is it? Well, okay. Now I'm going to have to get technical. Are we at rest right now? Why? Pardon me? More specific. How is the Earth moving? Well, first of all, it's round, so it's spinning. Okay? So, NASA built in Florida on purpose because it launches over the Atlantic Ocean. It gets a boost from the Earth's spin. Where would the best place to launch be then? On the equator. This is why Elon Musk is trying to build rockets that can launch from ships. What he's saying is, why don't we put ships right on the equator, launch them, you get a huge boost. This is why Russia had such a tough time with their space program. They did not have something nice and far south like Florida. And so even today, their rockets are just workhorses because they're not getting much of a boost from the Earth's rotation at all. However, for us to know what V initial is, we would need to know the latitude and longitude, and that would be a lot of work. So we are going to decide that our rocketry program is either Santa's Workshop or Superman's Fortress of Solitude. One of the two of them has a rocketry program, because we're always going to assume that we are launching from the... No. Santa's on the equator? Superman's on the equator? Where is Santa?
Where is Superman?
Where is Superman? Fortress of Solitude in the North Pole, my friend.
I know that.
I know you didn't. So we are going to say that, even though technically it depends where you're launching from, because the Earth is round. So, do I know M? Do I know V? They told me. Cool. What was the mass? Little m, so it's the satellite, 925. V was 3,917. Don't forget the squared. So the change in kinetic is going to be... Usually you'll find the change in kinetic is a factor of 10-ish smaller than the change in potential. Most rocket fuel is used to get the satellite out of Earth's gravity well, to the right altitude or the right height.
Good morning.
So I got 7.096 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8, 9. What? Aiden? Oh.
That's not that hard. That's easy.
Oh, this isn't the longest one yet.
You said that was the longest one?
I lied. The reason this isn't the longest one is they gave me the orbital speed. The longest one wouldn't give me the orbital speed.
Again. So a reminder for students there is...
What do you get? Plus, thankfully I have this, I can use answer button. 4.369 times 10 to the 10th. How much work? 5.08 times 10 to the 10th joules.
Or 07, not 08.
I used my answer button and I have an 8 next to my 7, but I was using my answer button all the way through. I would take zeros. As long as you're good to 2 sig figs, I'm good with this because we're doing some heavy duty calculations. You asked, what would the longest question be? Well, where they don't give me the orbital speed, where I actually have to calculate the orbital speed. Yeah.
How much are these questions worth?
This would be a written question worth 7 marks. Like every other written question that I typically give you on a test. Okay? We're clearly going to pause here. A bunch of you were away yesterday. You want to make sure that you have watched the orbital lesson from last day.